All right, so this is vectors in space. So it's basically the same concept, but just a three-dimensional space. So again, a nice little review of multivariable calculus. So given the x, y, z plane, and then some people do it differently. Some people put the y-axis here and the x-axis. It really doesn't matter, right? They're both flat. The z-plane is always the one going up and down itself. So points on the space. So space is just short for 3D plane, if you want to call it. So given a point P, it's in respect to x, y, z. So it goes up, across, and then above. So this way, and eventually up, right? It's in three-dimensional space. Okay. So lines in 3 dimensions in space, right? So given a line in 2 dimensions, right? It's just a straight line, x, y, z. So y equals mx plus b. Okay. Well, in 3 dimensions, since we have the third variable z, everything in terms of z-axis, meaning it's z equals something in terms of x and y together. So the nice thing about planes and lines and everything like that is a line in here is in 2D. Think of just add an extra layer, meaning it just goes out and looks like a paper. So in fact, that's exactly what it does. It just makes a paper. Well, it's a bad paper, but it makes a plane. Okay? And then that way we have depth, right? All going back to three-dimensional objects in multivariable. But we're not going to go too far into that stuff. That's, we already did that stuff. Now I'm just going to, what we did in 2D, we could do it in 3 dimensions, right? So the first part is the distance between 2 points in 3 dimensions. It's the same thing. If you notice, I just covered that up. It's the distance between 2 points. Now it's just 3 points, right? Give it a P and a Q. The midpoint is the exact same thing, right? This is the X, Y, and eventually now since we have the Z-axis there as well. Okay. So again, it's nothing too complicated and convoluted. Same thing when it comes to components of vectors. So in 2 dimensions, they're just, end minus start. And the same process comes into here, B1 minus B1, and so forth. And then B3, now minus A3 is the last component. And in vector format, exact same process, right? If I get rid of this, this is eventually just the vector in 2 dimensions, but now we're just having it in 3 dimensions. So that means everything we could do in 2 dimensions, we now do in space, right? So given points A and B, let's represent vector V as AB. And then let's see be that point. And again, find a point D such that we have this happening. Okay. So vector V. So 0 minus 2, 3 minus 4, and then finally 1 minus a negative 1 gives you positive 2. So there's our vector there. Okay. So this is part A. Now part C is given an arbitrary point, and notice we go from C to D. So this new vector V is going to be this minus this, right? So it's going to be, say, D1 minus negative 2, so just plus 2, D2 minus 5, and then D3 minus 1. And then we just set them equal to each other's components. And then we just solve for each individual variable, right? So D1, so negative 2 equals D1 plus D2. So subtract it over, you get negative 4. Same thing here. Add this over, gives you 4. And then finally D3, add this over, gives you the 3. So the point D would be negative 4, 4, 3. So again, same process you do in 2 dimensions. So from there, we can do add, subtract like normally. Right, just component, and then we have a scalar multiplication, which again is just v times itself. And same thing for parallel vectors. In 2D is the same process as in 3D. It's just a constant times the other vector, or we'll talk about a little later, a linear combination of the other vector. That's going to be a little precursor for later on as well. Okay. All right, so the last couple things is the length of a vector. Again, same thing as in 2D. right? To cover this up is the two-dimensional. Since we have an extra component, it's just an extra component there, which the same thing is now it's a unit vector is the exact same equation. So just doing some practice problems. So find the vector of that has length of 11 in the opposite direction and in the opposite but same direction of u. Okay. All right. So first thing we're gonna do is if we want to find define the same vector of it. So we're gonna take the unit vector of it. So we're just gonna find the length of u first. So this is going to be the square root of each component squared. So this squared is 4, this squared is 9, and this squared is 1. So the square root of 15. So our unit vector, which is the same, is parallel to this vector, right? Same direction means parallel. It's 1 over the square root of 15 times our original vector. Okay. However, that wasn't enough what we wanted, right? We also wanted that has a length of 11. Okay. So all we're going to do, since remember this is a unit vector, so this is a length of 1. Well, how to get a length of 11? Well, we'll just do 1 times 11 gives you 11, which means this times 11. So and we'll want opposite. We'll talk about that right now. So all we're going to do is multiply by 11. And the last step, since we also want opposite, we're just going to change the signs. So this new vector u is equal to 11 over the square root of 15 times the vector of 2, negative 3, negative 1. And you can put the negative here as well. I'll just put it in the vector since it's just I want the opposite vector itself. Okay. Right, and the last step is just like what it was for 2 dimensions, unit vectors in space, and the identity matrices in space, and identity vectors in space. Okay. So again, since we're doing space, we're going to be dealing with our identity matrix, which means we're going to have I, J, and K respectively. So ith component is 1 with a bunch of zeros, J is the one in the middle, and then K is the last one with 1. Okay. So again, like everything else, we can express vectors in terms of its I, J, K component, or the identity matrix itself. So like this one, so express the vector in terms of the I, J, and K component. Okay. So remember, we could rewrite this to look like this. Right. So it makes sense because this times this gives you negative 1 plus 0, because 2 times 0 is 0, plus 5 times 0 is still 0. And then same thing for the middle one, same thing for the bottom one. Or the more proper way you see the multivariable, like that.